Okay. Now that we have the integral test, we can solve this exercise related to that test. The other three exercises which come before this are the proofs of the various results we see in this section, which we have already done. Although there is still one more corollary left for us to see, but we will see that afterwards. Instead, let's just solve this exercise. What this exercise says is that both the directions of the integral test break down if the function f that we have in the statement of that test is not assumed to be decreasing. So let's recall the integral test briefly, what it was. So in the test, we have a function like this, which is non-negative and monotonically decreasing. Because it's given that f is non-negative, if you want, you can take this as the range. You can do that. Then you do not have to again write it's non-negative, but it is monotonically decreasing. That you have to mention. Then the test says that this infinite series is convergent if and only if this supremum is finite. Finite means it's a real number. This means that we have to provide an example of a function of this type which is not decreasing, for which this is true but this is not true. That means the series is convergent but the supremum is infinite. And another example of such a function which is also not decreasing, for which the supremum is finite but the series is divergent. So that way both the directions of the test will fail if this hypothesis is missing, decreasing hypothesis. So let's see how we can write a solution. So let us first consider this function. Define f from the set of non-negative real numbers into the set of real numbers by this rule. F of x is equal to 1 if x is a natural number and 0 if x is not a natural number. Let's take a moment to see what this function looks like if we try to draw its graph. Whenever you define a function like this, a real valued function of a single real variable, if you can draw its graph, then please do it. That way, if you see it in front of you, many things become immediately clear. So let's see how this function has, what type of graph it has. Because this, of course, is not a part of the solution. Because the function has the set of non-negative real numbers as its domain, so we do not need that part. All right. Now, if we plot the integers, roughly 1, 2, 3, and so on, and say we have 1 here. Now, what type of graph do you expect? The function maps almost every input onto the real number 0. So the graph is almost always the x-axis, except at the natural numbers. Because we considered 0 to be a natural number, at 0 the function has value 1. This. After that, as you move towards 1, until you reach 1, the function has this graph, which is this line segment on the x-axis without its endpoints, 0 and 1. The moment you reach 1, the function again has value 1. And then again, between 1 and 2, exclusive, the function has 0 value. Then at 2, again it has value 1. Again 0, again 1. Like that it goes. So the function is almost entirely 0 except at some isolated points. At those integral points, the value is 1. That's how the graph looks. Immediately from the graph, you can see one thing, that for this function, if you calculate, at least you can guess this integral for any positive integer, positive real number n, the integral will be 0. Why? Because there is actually no area under the curve, under the graph. There are only some isolated points which appear above the x-axis, but below a single point you just have a line, and that line has length but 0 area. Elsewhere, the function actually doesn't go up at all. That is why we expect that the integral should be 0, and it is 0. However, we cannot just vaguely say, oh, it looks like it will be 0, so it will be 0. No, we have to exactly show why it is 0. So that's where we need to carefully choose a partition. That's what we do next. But before doing that though, let us also note that this function is not decreasing. Why? Well, that's because the values fluctuate. Now, we have 1 and then 0, again 1, again 0, so how can it be decreasing? So we start by writing this. Note that, but it is still non-negative. No value lies below the x-axis, no negative value. F is non-negative but not monotonically decreasing. Okay. Now for any positive real number n, when we write something like this, you should in general understand that n is a real number. Just because we normally use capital N to denote an integer doesn't mean that n is an integer. That's not always the case. In a specific context, it may mean an integer, but in general, it's a real number. Consider it may be an integer, may not be an integer. The following partition of this interval. Why this interval? Because we want these integrals. Now I should write the partition here. The partition itself depends on whether n is or is not an integer. So actually we are going to consider two cases. But I am going to write like this. Say I call that partition P. Now you can perhaps guess how I am going to do the partition. I will isolate the integer points separately, and I will consider these intervals also. So these intervals will be my non-degenerate intervals in that partition, and the degenerate intervals will consist of the natural numbers. That's how I can isolate the 0 values and 1 values. So if I do that, it will look like this. A partition is a set, no? So I start by writing a curly bracket. First I isolate 0. That's one degenerate interval. And then the open interval 0, 1, this much. Then I isolate 1. And then the open interval 1, 2. And then I take 2 as a separate interval, and like that it goes. How far will it go? Well, at some stage, we will have this. You may think that this is not necessarily meaningful because n may not be an integer, but wait. This is the case where n actually is an integer. So that is one case where eventually we reach n minus 1, n, and then we end our partition with the right endpoint. It's like if you have n equal to 3, then you will have like this 0, 0, 1, 1, 1, 2, 2, 2, 3, and then 3. If n is a natural number. But if n is not a natural number, then what? That is why we define the partition itself partly, okay, in parts. In that other case, also we start as above, but we cannot end like that. 1, 1, 2, and so on. Okay, now we will, however, be able to consider an interval where we end, okay, and its endpoints are really integers. However, this time that has to involve the floor function minus 1, floor n. But then we do not have just one point more to consider. We have this interval instead. Closed floor n, hold on. No. Floor n itself is also an integer, so it has to be considered separately. Yes, and then after that also there is some room left for more points, and that's where you have open interval floor n, n. This side is closed. If n is not a natural number. Okay, so this, I should perhaps write P here. This is our partition. It looks quite complicated, but from the figure it becomes clear what we are writing. However, still, let me give you an example of this case. What type of case is it? If we take a specific value of n, how can we see that on the diagram? So for that, let me just quickly draw that figure once more. So it was like this. One, two, three, say this is one. Like this it goes. Say I take n equal to, keep in mind, n is a positive real number. It is, in this case it's not an integer, but it is still positive. It may be irrational also. Suppose I take n equal to 2.5. Not necessary you have to take the middle of any interval, say 2.7. So it lies here somewhere. Okay. So this is where you have your n. Then what is your floor value of n? Floor value of n is the greatest integer less than or equal to n, or geometrically speaking, it's the nearest integer to n that lies to the left of n, and that is 2, this one. So that is your floor n. Okay. So that means as you go on following this pattern, so if I actually write the partition for this, how does that look? 0, yes. Then 0, 1, okay. 1, 2. Then 2 also can be considered, but then 2, 2.7. Is that what we are considering? No, I think okay, hold on. Yeah, what have I written? 2. So 2 is this. Oh, so the other interval which comes before this is something else. It is in fact 1, 2. So from this point onwards, we consider this. That is, the floor value of n is 2, and then we consider n. So n is 2.7. I was correct in considering 2.7, but it will be like this. Okay. This is our second case, if we take this value of n. So it's really not that difficult also. It's just you go as far as you can go following this pattern, and after that, when you cannot go any further, you just consider whatever else is left together like this. That's the thing. Alright. Now, one thing that becomes immediately clear is this. Clearly, f is piecewise constant on 0, n with respect to this partition P. Why? If your case is the first one, we have to consider both the cases. If our case is the first one, and say for a moment that capital N is 3, then our partition ends like what? Then we would have here, after having all these things, we would have open interval 2, 3, and then singleton set 3. Now, on each subinterval of our partition, is the function constant? if we restrict it on that subinterval. Of course, some of the subintervals are degenerate and have only one point. So there, of course, it's constant. Elsewhere, on the non-degenerate intervals, the function is constant and is constantly zero, in fact. So that's the definition of a function being piecewise constant. Okay. So f is a piecewise constant function on 0, n. But next, let's consider this second case. For simplicity, consider this specific example itself. Is our f piecewise constant on closed 0, closed 2.7? Here n is 2.7. Yes, again, on these single points, of course, f is constant, constantly 1. And on these degenerate, on these normal intervals, non-degenerate intervals, the function is identically 0, so constant. On this part also, greater than 2 and less than or equal to 2.7 also it's constant and constantly 0. After all, it's piecewise constant again. So in general, f is piecewise constant on any such interval with respect to this partition. Alright. Now we are going to need this partition. Okay, so let me just keep this part as it is. Now because f is piecewise constant, we can find its integral very easily. So the integral of f on that interval is equal to the piecewise constant integral of f with respect to the partition P. But now, do you see that the integral will be 0? Yes, it will be 0. Why? If we have the first case, where things are much more uniform and they uniformly end, obviously the integral is going to be 0. What are the intervals, subintervals in our partition where the function takes some non-zero value? Those are the single points, degenerate intervals. There the function takes the value 1. So when you write this PC integral, what do you actually do? You of course multiply those constant values that the function takes on the different subintervals by the length of the interval and add them up. That is the definition of PC integral. So the places where you get 1 are the only places where you get non-zero function value. But then when you multiply those ones by the length of the corresponding interval, the lengths however are 0 because these are degenerate intervals. So you do not get any non-zero contribution from even the non-zero f values. But elsewhere, where you have positive length, there however the function value is 0. And that is why in the first case, this will be equal to 0. Is it also the second case? Yes. The second case is almost exactly as the first one up to this point. But what about this? On this interval, f is identically 0. Why? Because note that now capital N is not an integer. It's not a natural number, so it's not an integer. And that is why f is identically 0 on this non-degenerate interval. So here also we do not ultimately, taking everything into account, we do not get any non-zero anything. So this is also 0. And this fact is true for any n, any positive real number n. Thus, the supremum will also be 0. However, let us now see what the series is for this f. What is that infinite series? But So the infinite series involves the f values at precisely the natural numbers, and according to our definition of f, those are the points where f takes on the value 1. So this is just this series, all of whose terms equal 1. And we already know that this is divergent, because if you look at the sequence of partial sums of this series, then you just get the sequence of positive integers, which is not even bounded. How can it be convergent? Is divergent. So this is one example where the supremum is finite but the series is divergent. So integral test fails. So we see that if our function is not decreasing, then things can go wrong in one of the two possible ways. But now let's see the other way. Well, for that I need to erase this part because I cannot move that. So now we are ready for the second function. The second function is also similar to the first one. We are going to call it something else. Say, let's call it g. Next. But it's slightly different also. Oh, we can write consider, but let's write define. Define. Again, the type of the function is same, but the definition is different. By this rule, gx this time is 1 plus x to the power minus 2 if x belongs to n, and 1 if x does not belong to n. Okay. Now, if we similarly draw a graph for this function, let's see what we get. Here it's not exactly 1 and 0, but still the nature of the function is similar to that of f in one respect. Again, we mark out integers because the definition is like that. All right. Unlike the previous case though, now the function seems to be almost entirely 1. Okay, it takes on the value 1 almost all the time, except at some points where it deviates from that. Say when you have x equal to 0, 0 is a natural number. What's the value that we get? 1 plus 0 to the power minus 2, so 1 after all. Okay, so we do get 1 when x is 0. And then as we move our input towards 1, until we reach 1, it is constantly 1. So the graph looks like this. But the graph doesn't quite reach this vertical line because at 1 it changes. If you put x equal to 1, then this is, we have to use this part of the function. So it is 1 plus 1, 2, 2 to the power minus 2, that means 1 divided by 4. So here the value is here somewhere. Okay, 1/4 of 1. But when you exceed 1 and again start your journey towards 2, the function again takes the value 1 until you reach 2. Okay, so there is a break. The function is discontinuous at these points, at these integer points. At 2, you have 2 plus 1, 3, 3 to the power minus 2. So 1 divided by 9. So again another small value. And again you have a line segment like this. And that's how this goes. You can now see that the areas are piling up. It's not like the previous case that almost everything is 0. Actually you have areas under the curve. But at the integer point something else is happening. Alright. So let's now see what will happen to the integrals of this function on those intervals and what will happen to the infinite series. I kept this partition itself because now also you can see that under that same partition with both the cases available to us, G is still piecewise constant on that interval 0, n. Why? Well, because on those non-degenerate intervals, G is constantly 1. And on the degenerate intervals, of course, they have whatever value, it has whatever values it has. So it is piecewise constant. So that's what we are going to first write about G. Note that, I can write it here itself. Note that G is piecewise constant on, let me continue from here, 0, n. So we can calculate its integral easily, but we have to be more careful than the previous case. Now, integral of G over that interval is the PC integral of G over that interval. Alright. But this is where we need to carefully see what that thing will be. Okay. Now before I erase the definition of G, let us see what will happen in the simpler case where n is a natural number. Again, we have divided the interval into parts, the entire interval 0, n. What happens in each part? At the degenerate intervals, of course, the contribution is going to be 0 because you see, unlike the previous case, here at 0 the value is 1, at 1 the value is something else, at 2 the value is something else. There it was constantly 1, 1, 1. But that does not matter because the lengths of all these degenerate intervals are equal to 0. So they do not contribute anything, any non-zero thing to the PC integral. What happens to the non-degenerate intervals? On each non-degenerate interval, the function G takes constant value 1 and you multiply 1 by the length of the interval. All the non-degenerate intervals you can see here have length equal to 1. And how many such intervals do you see starting from this one and ending at this one that are non-degenerate? N number of intervals. So n number of ones you get and their sum. So in this first simpler case, you can clearly see that the integral is n. But is that also n in the second case? That's what you have to understand. In the second case, the first part is almost like the first case. We continue to get a 1 from this interval, another 1 because of this interval. Like that, we reach this interval. That also gives us a 1. So how many ones have we accumulated? Namely, the number of ones is the floor value of n, because 1, 2, 3 and like that up to this. So when you write the PC integral in this second case, this many ones you get, so when you add them up you get this number. But there is still, there are two intervals actually more. One of them is this degenerate one which is going to give us 0, and the other one is this one. On this interval the function is not 0, it is 1. So plus 1 times the length of this interval. What is the length? The right endpoint minus the left endpoint by definition. So you see that after cancellation it is actually again n. So in both the cases, here also we get n. Alright. Yeah, now we can erase the partition because its role is over. Oh, and I made a small mistake also in notation. Here it will be P. Alright, so you can now see that unlike the previous case, now the integral values are increasing. And for a given n, the integral value is actually equal to n. So obviously, the set of integrals is unbounded above. You can choose your n as large as you want. That itself will be the value of this integral. So you can write clearly here supremum of the integrals of g as n varies over the positive real numbers is equal to plus infinity. There is nothing wrong in writing equal to plus infinity because of the extended real number system we have already introduced. Okay. So supremum actually can take the value plus infinity. That means it's not a real number. However, what about the series? At the integers, we have this, right? That means we have not arbitrarily, carelessly defined the function g. We have defined it keeping something in mind because this series looks familiar. We know about this series. If you change the variable and write things like this, say I write m equal to 1 to infinity, 1 divided by m square, then this is a convergent series, and that comes from a previous result. But the series is convergent. Let's also refer that result, and that result was these numbers corollary 737. So this is the other case in which the supremum does not, I should not perhaps say does not exist, but it's not a real number, but the series is convergent. So in that way also the test can fail if our function is not decreasing. Note one more thing, that although just like fg is not decreasing, but just like f, G is also non-negative. G also, like f, does not take negative value as its outputs. So that's the exercise. There is only one more thing left in this section, which is a corollary, which in fact we already have proved before. It is that result from where this thing is coming. Do you remember this series where P is a real number, and the result that says that this series is convergent if P is greater than 1 and divergent if P is less than or equal to 1. That is the next corollary that we have to see, but the job is to use the integral test to get this corollary. So we will see how we can do that. So let me end the video here itself, and tomorrow also we have one upload. What shall we do tomorrow? Oh, we have already gone through trigonometric equations, okay, last week. So tomorrow let's go back to number theory again, where already we have proved Fermat's little theorem in one way, and tomorrow again we are going to see another proof, but this time using the binomial theorem. Okay, so let's see you with that tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.